The physics of a car turning can be a little bit confusing. Hopefully you read the document, and at the beginning of it I talk about the physics of a car skidding to a stop or accelerating really quickly forward. Whenever a car accelerates, it's limited by the force of friction. Even if it had really good brakes, a car couldn't skid to a stop if the road was slippery. Or even if it had a powerful engine, it couldn't take off and accelerate forward quickly if it was on really slippery ice. Similarly, how a car turns is affected by the friction. The sharpest it can turn, just like the quickest it could slow down or the quickest it could speed up, the sharpest or the greatest acceleration the car could have when it turns also depends on the friction. So for the first, always going to draw a free body diagram. It says it's a level roundabout. We're going to get to angles later, but for now, level roundabout. So the normal is going to be straight up. I'm going to draw it as if the car is turning to the right. Gravity down. And then I don't know what to call this. You could call this the force of the road on the car. I often call it the force to turn. The car pushes outward on the road pushes inward on the car. That unbalanced force on the car makes the car turn. If the road could move, the road would move outward. So if the car's turning to the right, if the road could move, the road would be pushed to the left. Typically roads can't move, so the road doesn't move, but by Newton's third law, it reacts and pushes the car. If we push the road to the left, the road pushes the car to the right, and the car ends up turning to the right. Every time we have an object going in a circle, it's going to turn into an F net equals ma question. In this case, the F net is what I'm calling the turning force, and because it's going in a circle, after the proof, we know that centripetal acceleration is v squared over r. So I get an equation that looks like that. Now this is a logic step, so it's going to look a little bit weird on paper, but when it's at its max acceleration, whether it's speeding up, slowing down, or in this case turning, when it's at the max acceleration, that happens when the turning force is exactly equal to the force of friction, the friction that we can calculate. If it's not turning as quick, it would take less force, but at the most it can turn, that's when the fastest or sharpest it can turn, the turning force is maxed out by friction. So really, we can say F friction equals mv squared over r. That sometimes bothers people because it looks like it's friction that's making the car turn. In a way it is. The car pushes outward on the road pushes inward on the car, but the hardest that the road can push is when it's pushing with the force of friction. After that, the car will start to slide. Friction is always mu Fn. That's going to be mv squared over r. Because we're in a boring case, that turns into mu mg equals mv squared over r. What's kind of cool is the m's cancel out. If I flip the r to the other side, I get this v squared equals rug equation. That I'm not going to memorize it. I'm always going to reprove it, but that's a common ending point for a car on a level turn. V squared equals the r, the coefficient, and the 9.8. For this particular question, we're looking at an r of 30 and a coefficient of 0.8. So our v squared is 30.8 times 9.8. When we're done all that, we have to square root it, and I get 15.3 is the speed that the car can go around that. Any faster and there's not enough friction, so the car will slide out to a larger radius. Any slower, no big deal. There's more than enough friction to make it go slower, but that's the fastest it could go. Faster would require more force, and there's just not enough friction to generate